Our next presenter is Lorenzo Mencattelli from Helicoid Industries. The exciting part in this talk really has, to me, has been the discussion, and if you heard me preach about biomimicry in the last several years, we're to a point where we can take advanced technologies to take these innovations and actually start manufacturing them at scale. So that'll be part of the discussion there. A little bit on our speaker. So Dr. Mencattelli has a PhD in Aerospace from Imperial College in London, so no slough there. And then, in addition, degrees in Aerospace Engineering from the University of Pisa. Very much focused on IP strategy and leading R&D into that translational work, scaling up activities, and looking at innovations in multiple industries from supply chain, digitization, innovation of composite technologies into EV mobility, hydrogen storage, urban air mobility, and bio-based composite structures. So pretty much every single thing that this institute is interested in working. So I'm very interested in hearing what you have to say. Thank you.
Thank you very much for the nice introduction and for having me here today. So this talk will be focusing on structural type of material, lightweight composite materials, and the use of biomimicry is really trying to abstract some of the principle and lesson learned that we can have from natural materials and understand how to apply them to man-made materials. So the first slide this think is super important if you want to be successful in bringing this type of concept into man-made structural materials, is to avoid a direct mimic of whatever we observe in nature. But what is really important is to really understand the feature property that are observed in natural materials and how those are related to certain functionality of that material. And just to give you an idea of why that is if we look at man-made material, usually, they strive for high performance. They're single performance centered, whether it is stiffness, strength. They require very high energy for production. They use expensive constituent, and we design our structure not to fail, right? We don't want to have any damage in our structure. Our material kind of designed to be perfect, with no flow, no damage whatsoever. So we strive for purity, symmetry, and homogeneity. And the example that you see here is a single crystal blade of a turbine. Nature does not design high-performance materials, it designs high-performance structures. So you've got multifunctionality is a key feature. You tend to use constituents that require very low energy for production. They're cheap, recyclable, and it designs structure to resist failure, not to avoid it, but to resist it. And in fact, features which are critical to that are the heterogeneity in natural materials and randomness. In fact, the fact that these structures are often heterogeneous leads to a capability of achieving very high toughness levels. So very basic knowledge, toughness is a measure of a structure of being capable of dissipating energy before it reaches a catastrophic type of failure. And nature is able to do that by activating a wide range of energy dissipation mechanisms. I'm not going to list them one by one here, but it's to give you an idea of the range of tools that are available to achieve very high toughness values. And at the end, you reach material toughnesses, which are order of magnitudes higher than the single constituent toughnesses. So when you look at man-made material, a very common heterogeneous man-made materials that we use often today for structural applications are fiber-reinforced composites. What you see here is a generic micrograph of a carbon fiber composite embedded in epoxy. You can see the fiber, you can see the resin. So you've got long fibers that carry the load. You've got the resin that keeps the fibers all together and allows for the load to be transferred across the fibers. Its material is very light, stiff, and strong. So it tends to replace, in many applications, metallic type of structure. So the problem that we started that we wanted to address related to fiber reinforced composite was the fact that they tend to have a very poor impact performance. They tend to be very brittle and dissipate very little energy. And this is a problem that affects a wide range of structures, ranging from wind rotor blades, hydrogen pressure vessels, automotive component, aerial structures, down to sporting goods application. So the reason for that is that in conventional composite, we tend to use brittle reinforcement. They tend to localize damage very easily. They have a poor energy absorption, and in turn, you achieve a very poor impact resistance and structural integrity. And as I mentioned, as a result, we overbuild the structure, right? We apply huge safety margins to avoid any type of damage to occur in the structure that could lead to a catastrophic type of failure. So what you see here in the slide is what nature can give us. And actually, you don't see a single example. You see many of them. And that's because one of the other key features that I found it very interesting is to look for recurring features that are found in different creatures, and they kind of converge to a unique functionality. And here you see different are reported from the animal world, but there's also from the plant world. But the common features here is that the exoskeletons, protective equipment of these animals, they all share two common features. The one is that they are fiber-reinforced composite, and the second one is that these fiber-reinforced composites are arranged into helicoidal type of layup. And specifically, we focused our attention on one of these creature, which is the mantis shrimp. So what I'm going to show you here is a video where you have the shrimp on the left side, you have a crab on the right side. The shrimp is a very aggressive animal, it's a predator, and it's fighting against the crab, and you see it deploys these clubs like a hammer-like weapon to strike prey it feeds on, and you can see the shell of the crab being completely cracked. So crab shells continue to be quite tough material itself. It's a nacreous type of material. So it means that this ductile club needs to have a very interesting features inside that helps to sustain multiple impact and never incur into catastrophic failure. And if you look inside the club, in fact, what you observe is that, again, it's fiber-reinforced composite arranged into this helicoidal type of structure. So these translate very easily, if you want, to a man-made composite, where usually man-made composite, you rely only on a few ply orientations of the fibers when you create your laminated structures. They tend to use very large interply angles, usually larger than 30 degrees, like a common fiber-reinforced composite layup. Quasi-isotropic is at 0, plus minus 45, 90 layup. Very typical, industry standard, too much of a standard. And in this helicoid design, what you have is you have a smoothening of the change in fiber orientation across multiple plies, and this is where the abstraction takes place. So our intention is not to mimic directly the microstructure of the club, because there you have a change in fiber orientation between 1 degree and 2 degrees, which are not feasible at all in any industrial application. But to understand what that smoothening of change of fiber orientation brings in terms of mechanical performance, stress distribution, fracture mechanics. So that's where the research has gone for most of it. So the key point as well is that, again, is a high-performance structure. So we are not designing a new fiber, we are not designing a new resin, which means also that this technology is raw material agnostic. You can apply to carbon fiber, you can apply to glass fiber, meaning that you can deploy it in aerospace applications, but you can also deploy it in high-volume automotive applications. So the breadth of the reach of these type of tools and technologies really, really wide. So the next image that I'm going to show you, if you recall the mantis shrimp fracture surface, this is actually carbon fiber embedded in epoxy. And it resembles very closely the fracture surface of what you observe in the mantis shrimp. So it means that by leveraging this knowledge on how to arrange these fibers and obtain the benefit of the natural microstructure, you kind of have a very nice translation, even though you are not doing a direct mimicking of the features found in nature. So we have a quite high TRL and MRL validation of the technology. We are launching this year in sporting goods. It's a low-hanging fruit, very short validation cycles. With CCM, it's a major sports brand here in North America for ice hockey. So we are launching the technology in their blade to improve durability, impact resistance. You would be able, it's already in production and it's going to be into the shops in a couple of months. The other company based in Michigan is Revolin. They produce pickleball rackets, fully made with they're fully bio-based. They're using bio-based PP and natural fibers, flax fibers. And we are deploying the technology into the skins of this sandwich structure, basically, to again improve sweet spot during the game and the durability of the racket as well. In automotive, we are launching the technology in EV cars, specifically in and I will give you an example of the performance in these applications. Underbody protection panels of an EV car is basically the only physical barrier that you have to protect the battery pack from the road. So it's a critical feature, and we are working with TPI Composites based in Rhode Island and several raw material suppliers to deploy this at scale. Defense application, we have a few SBIR projects with the Department of Defense as well, where we are trying to address some very, very challenging applications for composite materials, a highly loaded component that needs to sustain, again, multiple impact in a very harsh environments. And our technology, it's showing that can bring considerable benefits there. To give you the example on the EV battery enclosure, as I mentioned, we are using the technology on the protective panel, the bottom panel that separates the battery pack from the road. And this is, we are showcasing this in 2 weeks in Atlanta at CAMAX. It's a big show for composite materials. You might know it or not. The big benefit here is you can see how usually you need to make a compromise between performance, cost, lightweight, but here we are striking through all the key points. You're basically developing a solution that brings you improved load-bearing capability, reduced damage resistance, cost savings, lighter, and that big advantage, the advantage that you see there in residual clearance is related to what happens after you have encountered the first damage in your structure. Let's say that you had an impact in the underbody protection panel. The picture that you see here with the schematic of the battery pack is what the panel, the helicoid panel looks like after the first impact. So it springs back, it recovers completely the initial deformation. There is no permanent dent, no fiber failure. Everything is contained within a matrix failure into the structure thanks to this bar-inspired architecture. And this is what happens in a metallic structure, which is the commercial reference at the moment, where you have a permanent dent, meaning that a secondary impact would for sure damage the battery pack. And if you have seen videos around of what happens when you damage a battery pack of an electric car, it's pretty nasty. So in aerospace, it's the long haul, challenging space for startups, a very long time to revenue, and difficult to change the mindset of how things have been done for many years. But we are testing with 2 primes for engine containment casing. It's a spot-on application for our technology. We achieve a plus 30% improvement in ballistic limit using carbon fiber, which is amazing. You usually need to move to very expensive and type of reinforcement like para-aramid, ultramolecular weight polyethylene that comes with a series of complexity and less structural functionality. We can do that with plain carbon fiber. We have a couple of big R&D programs where we are trying to understand how this could be beneficial also for standard damage tolerance type of applications, so wing structures, airframe. We're doing a lot of work also in the eVTOL space. And military, we have applications and work ongoing with Northrop Grumman here in the US as well, where we are working with them again in how to translate this type of new design into projects that usually last 20 years plus, right? So it's not easy. Above and beyond, mechanical performance is one aspect. What I didn't get into much detail, just in the interest of time, is how we are able to achieve this great performance. One of the reasons is the capability of dissipating energy via only breaking matrix in the composite, and you prevent the fibers from failing, or you delay fiber failure depending on the type of impact energy you're using. But this means that even if you have damage and you're able to reprocess your matrix, for instance, using a thermoplastic matrix or using a V-trimmer type of resin, you're able to recover completely your damage. So you don't have to make a cutout and a proper repair of your structure. You can just heat it up and recover completely the damage. We have an interesting application in erosion. Key issue for wind rotor blades. After a while, especially offshore wind blades, they tend to suffer from rain erosion. It causes the damage that you see in the reference material. So the erosion is so harsh that break through the entire structure of the blade. So it's no more a problem of aerodynamic efficiency, becomes a problem of structural efficiency. You need to stop the blade, and that's it's a huge cost for maintenance. And on the left, it's what we are able to do with our tech. High temperature material, we are trying to reduce cost of using 3D and 4D woven ceramic structures using 2D type of laminate sequences, using our technology to recover the very brittle behavior of this type of material. Now I'm going very quickly because I see it's already red. In terms of enabling sustainability, is again material agnostic. There is one material that is gaining traction in the industry, which is linen flax fibers, especially in Europe, in the US, hemp fiber. But unfortunately, you see from this plot, it's much lower performance than a conventional glass fiber material. If we use our technology, you see that we can replace 80% of the mass of a glass fiber composite with flax fiber and achieve the same performance, so mechanical performance. So this is an entry point for this type of material into structural applications, which at the moment is not possible. And you find it only in non-load bearing applications. We have a DOE fund here as well, where we are trying to deploy this at scale in automotive components. So overall, again, what I showed you is it's a proven performance scalability of Biomimicry type of composite materials. It can enable sustainable solution. It has a very versatile value chain integration. I haven't spent much time here, but feel free to ask questions later on. It doesn't cause any supply chain disruption. You can use the same fiber, the same resin, the same manufacturing process. It's just a more intelligent way of designing structures. It's a technology platform. I've heard that already today, so I'm glad to say it again. You can use it to improve a range of products within a company's portfolio, and not just one single application. And we're always looking for partnerships, development of prototypes to prove the performance in any applications you might have. So thank you very much.
So many messages in there. We can take up some of them in the question and answer session. But I think to me, a huge takeaway there was to be able to use very low cost materials, natural materials, and just the way we arrange them, get very, very high performance products. And it's that structural aspect that is key.